What I'm going to talk about today in a lot of our customers that are building very large high-performance computing systems, they always have the challenge of how do they interconnect all this compute and storage and whatnot. And there's always a debate about which technology are they going to use. You've got Ethernet, you've got Infiniband, you've got some other things. So I'm not here to say that one's bad. I'm just here to talk about what we do, which is Ethernet, and why we think Ethernet is a very good option for building next generation high-performance computing networks. A lot of this is, we've heard mention of the cloud, cloud economics and cloud scale. One of the things that's important that's going on with that is that it is driving, while there may be differences in the workloads that we see in HPC versus the cloud, it's definitely driving the economics of how we build and have different technologies available to build these networks. So let's get right into it. Obviously, a lot of the goals around HPC, everybody in here sounds like they are very familiar with this. I spend a lot of time, my time, I'm out of the Houston area, so obviously I cover a lot of the big oil and gas companies, so they spend a lot of their time and effort on where they go punch holes into the ground. And a lot of this is either you've got a lot of systems with GPUs, or the Xeon Phi is very popular in terms of being able to build these visualizations. NASA is also one of my customers down there, so they do quite a bit around computational flow dynamics. But again, the common theme here is that we've got very large computational problems that we're trying to solve, and in general, we're trying to use commercially available hardware and software, build a very large collection of systems to go solve these problems, and overall kind of balance, to some degree, the cost, performance, and time that it takes to build these. One of the reasons why, again, that I think that this is important to bring out is that as we continue this path for building larger and better and more capable high-performance computing systems, having commercially viable and available solutions that are in the market are going to be important. And Ethernet has proven time and again that it continues to be the most viable from a high-performance interconnect system. So just a couple of interesting things of note. This is as of June 14th. These are not mine, my data. I took this from the president of the Ethernet Alliance, who compiled this. But if you take a look at all of the top 500 supercomputers out there that are reported, the most predominant are Ethernet and Infiniband. There's some of the proprietary ones like the Cray, Aries, and Gemini, but predominantly we see Ethernet and Infiniband. Out of those, roughly, it's about half and half today. Obviously, a lot of the government-sponsored, I'm very familiar with the Stampede supercomputer at TAC. Down in Texas, and obviously that's a very large Infiniband one. We see lots of those national labs, research institutions, and things like that going Infiniband. However, about half of them are still based on Ethernet. So if we take a look at it though, and break it down by industry and by type of entity, the vast majority of those are Ethernet. Those are commercial enterprises. So Ethernet is still very heavily used in the top 500. In particular, I've got one very large oil and gas customer. They've probably got I think it's number 75 is one of their cluster computers that they have on the list. They've got another part of, it's basically a different generation of technology that they've implemented. One was Haswell, one was Ivy Bridge and whatnot. Usually these, in the commercial world, it's the vendor that's actually doing the reporting to the top 500. It's not the company, because they're all competitors. They don't want to necessarily give out all their details. But one in particular, like I said, it's got number 75 and number, I think, 80 something on that list. And we see that this trend kind of follows this whole notion that Ethernet is very viable. There's a lot of people that know it. It's easy, it scales, and it does a lot of very interesting things. Again, not to say that Infiniband can't do that, but right now Infiniband is really kind of a one-horse race, right? And with some of the things that Intel's doing, What's that going to look like in the future? We don't know. I would be scared if I was the one company that's doing a lot of that, because Intel, I think, is about to eat their lunch. Again, as you take a look at it, by industry segment that uses Ethernet versus InfiniBand, the ones that are all industry, it's predominantly Ethernet. So, interesting data notes. So, my point is that we don't want to count Ethernet out. Yes, if you have a very large cluster computer using InfiniBand, it's going to work very well in MPI applications that are written to take advantage of RDMA verbs, and you're doing very small message sizes, and you're doing like these ping pong, or you've got these collectives that are doing like a gather scatter. That's all going to work really well over InfiniBand because it's extremely low latency and it looks great. But when you start scaling up to very large numbers and you are running different types of jobs and processes across this, Ethernet can perform very well. So some of the things that we see with being able to do TCP offload, being able to do kernel bypass, those are probably some of the most important things when getting Ethernet to perform at the same level that you would expect out of something like InfiniBand. And then since you can run RDMA verbs, you don't really have to change your application once you've developed it to be able to leverage that. You can do it over IP with iWarp, and also since Rocky has come out now. Granted, I don't know if anybody in here ever makes it out to the supercomputing. I had the opportunity to talk to one of the guys from Purdue when Rocky very first came out. And this is the ability to do, RDMA over converged Ethernet and get a lot of the advantages that you get from InfiniBand, but being able to get that over Ethernet. And they had a lot of challenges early on. Now V2 is out. This is routable Rocky. We can actually do a lot of that over IP and over UDP. So you now get a much higher scale, but still get all the same benefits that you would expect out of doing high performance computing when your applications are written to use MPI and RDMA verbs. So my point here is there's a lot of, talk that goes on, Ethernet versus InfiniBand. Again, I don't want to knock InfiniBand. It's just that Ethernet has proven over and over that it's a very viable technology and it's not going away. And it has very many advantages that we'll talk about. So one of the things that's interesting is now that we've got commercially available silicon from Broadcom and Intel has gotten into this game, we're starting to see that the networking is starting to keep pace with Moore's Law. For a while there, the network was kind of lagging what we were coming out with from a processor and compute capacity perspective. But just to give you an example, about 3 years ago, Broadcom came out with the Trident Plus ASIC, system on a chip ASIC, that we can build, and we're not the only ones that have access to this. I know Dell and others have this as well. But you can, out of that chip, you can get 64 line rate 10 gig interfaces. Well, within about 18 to 24 months, they came out with their T2 chip where same size chip, same power draw, same footprint, but doubled the performance. So again, we're starting to see the network and network silicon start to keep pace with Moore's Law. And hopefully that bears, and continues on for a long period of time. But one thing that you're going to see here is that in the next generation of silicon that's going to be available, a lot of people that keep track of this stuff they know that the Jericho chip is out now. You've got Tomahawk, which is another generation. We have T3 that Broadcom is going to be coming out with. And all of that is just really driving up the density that we can do 100 gig, 40 gig, et cetera. So lots of things that are coming that are going to enable 100 gig and 400 gig based on 25 gig lanes, and be able to scale that up quite a bit. So the other interesting thing that's happening that's going to enable this is when PCIe 4 actually is out and available. So a little bit of delay. I think they were expecting it late 2014, early 2015. There's been some delays in it. I think now it's probably most likely late 2015 or into 2016. But the whole idea is we get to 2 gigabyte per second lanes that allows us to really get that bandwidth coming out of the nodes very fast. We'll be able to do 100 gig, multiples of 100 gigs to and from systems. And this is not to say that we don't get that with PCI 3.0 today, but when you've got a CPU that only has X numbers of PCI channels coming out of it, you've got different things you've got to interconnect with. So, but this is exciting when that comes out. So when you take a look at what the Ethernet roadmap is, not a lot of people realize Ethernet has actually been kind of ahead of the game for a little bit. 100 gig Ethernet's been available for probably 3 years. We've had it in pretty high density for well over a year and a half. Within the next, few months through the end of this year, you're going to start seeing very high density 100 gig available across the board, and from other vendors too, not just from Arista. But this is where we get to being able to shipping en masse 100 gig. We've been doing 10 and 40 gig quite a bit. What's interesting is if you go look at a lot of the benchmarks and tests that have been done that compare Ethernet with Infiniband, doing Rocky and iWarp, that information is a little bit dated. A lot of that comes out of the Ohio State University here. I think his name's Dr. Panda. They do most of the work and really good work on coming up with that. But it's a lot of it's comparing, say, 1 gig or 10 gig Ethernet to FDR Infiniband. Well, obviously that's a huge difference to compare. 40 gig, 100 gig is out. The challenge has been who's got a 100 gig network card adapter that does all the offload or does Rocky, things like that in hardware to where you can bypass the CPU and stuff. So that's, hopefully those will start to hit the market pretty quick. But as you can see, we have a pretty good roadmap, 100 gig. We're about to really hit it en masse, and then with a very good path to get to 400 gig pretty quick. So one of the things that Arista is doing, I think Arista, Intel, Google, several others have joined together and are pushing this 25 and 50 gig Ethernet. And it really kind of gives us a sweet spot. What's interesting is, especially in the oil and gas industry, I've got very large HPC systems that are all still 1 gig attached, just because, the activity that they do on the network, they pull down a big chunk of data, they process it, generate the results, and put it back. And for a very small period of time, they're actually hitting the network. So it's not this, constant hitting the network at the same time. But as we scale up the performance, and we take a look at what it takes to manufacture and come up with these interconnect technologies. Of course, Infiniband uses a 25 gig lane today as well. But we're moving up to that because it's still, it's either a single wavelength or a single, light that we're having to produce. If we can jump that up from a serialized data perspective up to 25 gigs, then, that creates this sweet spot in terms of how we do that. So today, if you had 10 gig and you wanted to do 40 gig, you're doing 4x 10 gig lanes. If you wanted to do 100 gig, you're doing 10x. And then when you move up, it's really about moving to a 25 and 50 gig. But the reason why we show this is compared to 40 gig, the costs don't change in terms of what it takes to produce these. So we're now pushing this pretty hard, and we're not the only ones. You're going to see a lot of this. So I think moving from 1 and 10 to 25 is going to be a really good spot to be in terms of building, good systems. Everything's pretty much the same. Still uses the 802.3 Ethernet framing. Very good economics that are going to make it possible. And again, I keep coming back to that because we need good commercially viable solutions to kind of continue this model. Things that they may perform well, be very good technical solutions, but do they have staying power in the market? One thing about Ethernet and IP is, it is the convergence medium of choice, right? We've seen this when, back in the mainframe days, pulling, that was really, at the time, mostly around IP, but Ethernet has become kind of the de facto, medium for IP. But for voice, for storage. Now we're taking a look at in the HPC world, there's quite a bit that is converged. And you know, before I came up here, I was looking at some reports just to kind of compare market share information. We've had the last couple of years that were pretty decent for Infiniband, and you know, Ethernet obviously with everything that's going on in the cloud is just, you know, skyrocket in terms of a growth rate. It's very good, but we're seeing kind of a point where those are going to cross over, and Ethernet is going to continue to offer very competitive, very comparable performance capability, lower latency, and be a very good viable option. And you know, where does that leave you know, other technologies? We'll see. Intel's got some interesting things going on with their Knights Landing. Is anybody familiar with what they're doing with Knights Landing? You know, obviously they've acquired QLogic's Infiniband business, and you know, they're doing some interesting things with it, and they're going to integrate that into the Xeon Phis, next generation of the Xeon Phi. So that's an interesting architecture. We'll see where that goes. So, moving on. One thing about it that the reason why I have this slide here is in very large HPC environments, we see these huge, massive HPC systems that are built on a lossless fabric that uses what I call a positive feedback mechanism in terms of how do we ensure that as we send data between systems, we don't lose that, okay? The problem with those systems, they work very well. They'll make sure that you don't lose data, but you can quickly get into a scenario where if you've got any kind of congestion or issue going on, you have the potential to turn the entire fabric into a large blocking system. And it just keeps, you know, cascading. This has actually been one of the problems that I think some of the really large Infiniband shops have run into. It's kind of a constant, you know, thing that they've got to work on, is how do we tune it, how do we make it efficient and don't get into this problem. So, you know, in an Ethernet world, we've kind of come a little bit backwards, where it was this best effort delivery medium, but now we're trying to put storage, we're trying to put other things on top of that medium, and those things are not very tolerant of data loss. So, you know, how do we provide some lossless mechanism on that? And that's where we've come out with a couple of new IEEE standards to data center bridging to enable that. What Arista's approach has been, it's kind of unique. We're pretty much the only ones that have been doing this, is there's always going to be these scenarios where you have the potential for congestion in the network. And how do we handle that? You know, not to say that you still don't use these mechanisms to enable a lossless environment, but there are some additional things that we can architect the overall, each individual system and the overall network to perform better. So buffers and the ability to buffer within the network matters. Now, obviously, if you care about latency and you're buffering, well, that's not necessarily a good thing. So, you know, there are certain applications that you want to ensure that you don't have any types of congestion, you don't run into issues of oversubscription. That goes into the design of the architecture overall. But some of the scenarios that we see in cast, if I've got a lot of systems talking to, you know, storage that only has a few ports in it, or, you know, this is the common scenario because it's very expensive. If this is a top of rack switch and, you know, you've got a lot of systems that want to talk, you know, you're aggregating, you have some level of oversubscription. This is an area where we introduce potential congestion. The other area is where we have speed changes. Like if we're going to a 40 to a 10 or 100 to a 10, something like that, you know, there is always a certain amount of buffering that goes on, because we can't, you know, at a consistent rate be receiving serialized 100 gig data stream and make that match without, you know, buffering it up, receiving it all, and then serializing out a lower speed leak, and vice versa. Okay, so there's always an area, these two are the primary, where we're going to introduce some amount of buffering. So In our architecture, we typically do these for very large Hadoop environments where latency is less of an issue, but very consistent performance and jitter is an issue. They want to ensure that it's very high performance. You don't have a lot of inconsistent jitter and things like that that go on. So what we do is we build a lot of buffering capacity that is connected to the switch processing chips that are on our line cards. We can get up to 3 gigabytes of external packet buffering memory per packet processor, 18 gig per line card. Our highest density card that we have today, you can get 6 of those packet processing chips on there, each with 3 gigabytes. And then we've got kind of our normal way that we carve up that memory just for the normal operation. But if you have a microburst, if you have some event that all of a sudden you're accessing a very large amount of data and you don't have full non-oversubscribed design or architecture, we call that microbursts. How do we handle that? And so we want to be able to, if you were to chop this up, this memory across the available ports, or fully kind of amortize that memory across the ports, it works out to about 125 megabytes of buffer capacity per port. So that's a lot to be able to handle, these quick spikes and peaks. But obviously, if you're running a sustained load that is different than what you have capacity for, you've got a couple milliseconds there before, you're going to be dropping packets anyway. And this is before we apply, things like priority flow control on top of that to really make it lossless. But this architectural approach, we have very solid data that shows we can take a network that may be performing well. We're relying on higher level protocols to, understand that there's been some data loss. Do we need to retransmit, packets and things like that? But if we can eliminate that, we can make the network perform much better, much faster. So I'll not bore you on this. This kind of goes into a little bit more in terms of, how we break that memory down and how much you have. I mean, by default, the different queuing architectures that we have on this is, most switch vendors implement some sort of what we call virtual output queuing architecture, and that is just that you've got dedicated ingress queuing for every egress port that you have to use. That way, if you've got one port that gets very congested, it doesn't slow up data that's destined to every other port in the system. So it's common, we're not the only ones that do it, but you'll never find anybody that has this much capacity in it. If you're normally using that quite a bit on a sustained rate, then probably a good idea to go back and take a look at the architecture and how it's set up. But in general, in a lot of our customers, we do see these spikes happen a lot, where normally every time one of those spikes would happen, you would drop packets and not a big deal, you would just retransmit. But what penalty do you pay in latency related to the fact that the upper layer protocols have to realize that there was a drop and then go retransmit? And then you've got to go through, if you're not doing any kind of TCP offloading, regardless of that, if you don't have TCP tuned or optimized, you've got to go back through the kind of the slow start process of it. So you lose some efficiency in that. So these numbers are actually come from one of my large oil and gas customers. Like I said, this particular customer I think has at least the latest processor, which I think is the not Romley, but the late, I can't remember what it is, but these numbers are based on that. And so we have the ability, one thing that's really unique with us is we have the ability to get very granular, proactive view of buffer utilization across all our ports. So we collected this information and took randomized samples of when we use buffer per port and for how long, and looked at that over a duration. The max that we saw a port use up to almost 210 megabytes of buffer. Now, obviously, that's a very quick spike that we see on the network. We handle that. We eliminate the dropped packets for that period of time, and they continue on. On average, ports, if you were to average it out, we're using about 19.8 megabytes. And 35% of their ports actually required greater than 12 megabytes of buffer. And in their case, they've got a pretty solid architected network. I think they're looking at probably a 3-to-1 oversubscription ratio from the bandwidth that they have facing down to the nodes within the rack, pretty dense racks, and then 40 gig up to their spine layer. If you look at a lot of the commercially available silicon that's out there, there's 12 to 14 megabytes for the entire system on a chip. Okay, so we're using the Broadcom in this platform that gives us these deep buffers. We're using a platform that allows us to connect external packet buffer memory and increase that where we're giving 125 megabytes per port. So in comparison, where some are putting these switches in place that give you 12 to 14 megabytes for the entire switch, that's for the equivalent of 64 or 128 line rate 10 gig ports, we're giving you 125 megabytes per port, per 10 gig port. So quite a bit. But this just kind of shows that deep buffers really help. Now again, this is before we layer on any kind of lossless mechanism. If you put the two together, it works really good, because if we can handle a lot of that down here, we're not having to deal with all the overhead of systems having to tell each other how much buffer space they have left to be able to do it. So this kind of gives us a good view of why it's important. So as we take a look at, and these are some of the different things that we've tested with, and the maximum buffers that have been used in a typically architected network, right? Where you're not going for the full, complete, non-oversubscribed environment, where you, in that kind of scenario, in a perfect world, you don't want to do any buffering, right? Because you should have, for every channel down, you should have a dedicated channel up. But in this case, it's your typical, close to 3-to-1 oversubscription ratio, and some of the numbers that we see based on the different applications, whether it's storage, whether you've got build servers, or running a Hadoop environment. What you see is, as the degree of incast or oversubscription increases, we see that with a shallow buffer system, that your actual good put almost linearly kind of degrades in its performance, versus a deep buffer system that is able to handle that and continue a very good level of performance throughout that. We've actually written a really good white paper. One of our founders, Andy Bechtelsheim, this is a lot of the work that he and research that he does in terms of figuring out how we should design our switch architectures. So if anybody's interested, that is a very good white paper on high performance computing and deep buffer switch architectures. So this is another interesting tidbit that literally, of course, this isn't your typical HPC type environment. This is more of a cloud operator, but data SIP, and his comment on it. But we literally, the latency that we would see is around 15 milliseconds, and this is obviously, this isn't. Don't look at this and think, oh, 15 milliseconds is really bad. This is their application, right? So it's different than looking at it and saying, hey, I should be getting 200 nanoseconds, through a box or something like that. It's you got to consider this is their application and the way it runs. But literally, they've got one brand of switch that is connecting their systems together, and they're running about this 15 millisecond level of latency. All they did was switch that out for a deep buffer architecture switch from Arista, and boom, had a pretty dramatic drop in latency down to 2.2 milliseconds. So this is really important. It sounds simple, and a lot of people may not put a lot of weight into it, but we've got very good data to back this up, and a very solid white paper that kind of talks about this architecture. And then if you layer a lossless mechanism on top of that, like priority flow control, where you can say, I'm going to identify what traffic that I don't ever want to drop. And that's where we're going to make sure to send. It's what I call kind of a negative feedback model versus the buffer-to-buffer credit system that you see in Infiniband and Fiber Channel. This is feel free to send me everything that you can send me. I'll let you know whenever I'm getting congested, and please back off. And we can do that by traffic class. So that goes back to the whole idea around convergence, and why Ethernet is such a good medium for convergence, is because now if I'm building a very large system, I can build it based on one type of network technology. I have one type of investment in terms of how I interconnect all of this, and it functions very well in terms of being able to manage all those different types of applications that we send over it. I may have one, like typical web, transactions that are going on that, hey, if we lose one, it's okay. TCP will recognize that and retransmit. But I've got storage data, or I've got my MPI, RDMA-based application that I don't want to drop anything. Well, we can identify that in its own traffic class and make sure that that one gets backed off if there's any congestion, so we don't overrun buffers. So just in general, where are we going from evolution on the uplinks? This last year, we introduced the first 100 gigabit Ethernet top of rack switch that was available. Do we have a question?
For oversubscribed channels, how deep can you actually go?
I'm sorry, I'm hard of hearing.
For oversubscribed channels, how deep can you actually go?
The reason that you have a buffer of 500 MB, wouldn't that increase the latency?
Yeah, I mean, if your application is going to run at a very high sustained rate, and you expect low latency, yeah, that's not a good thing, right? So, the idea is that if what is causing the congestion, is it a high level of oversubscription? If it's okay to define a high level of oversubscription if the application you're going to run over it doesn't push that uplink bandwidth, to its capacity. Does that answer your question?
No, actually I was thinking about the size that you mentioned about the buffer, 500 megabytes. So how large can that be? Because at some point, addressing such a big memory would take more time than to actually transfer.
Yeah, I mean, obviously if you're, we're looking at using that across usually a high number of flows. I don't think we have any data that gets it down to, let's say it's just a single flow, let's say it's all, MPI, scatter gather operations that are going on. You probably wouldn't want that to be, super high, right? So I can take that down as a question to go, look into to see if we've done any work around, how high do you want that to go? I mean, the default TCP retransmit timer, you certainly don't want to buffer it up to that point, because you might as well let TCP drop it and let TCP figure it out. Once you get to that threshold, then, it's not much benefit for you. But the idea is, at least in your typical TCP-based applications, which I know is in high-performance computing, you want to move away from the socket-based, applications to leverage MPI and RDMA verbs. But, in that mode, the idea is that we're trying to reduce the amount of time and inefficiency that you get from that.
Just like you showed the benchmarks for Ethernet, like the evolution, and we are lagging behind. Is there something like a roadmap for PCI? Is there a PCI roadmap? When do you?
So PCI, well, I showed the one slide. The next generation is the 4.0. I mean, we're expecting that here in probably late 2015, 2016. The Dell guys probably would have a pretty good idea of when they're going to start shipping that, and obviously Intel on when, what generation of processors are going to come out with PCIe 4 channels. So, but I expect it to be probably late 2015 to early 2016, something like that. Is that what you guys are seeing too? Where it goes beyond that, I don't know. I'm not. I don't really keep tabs on the PCI SIG. I haven't seen one. The only when I get out there and look at the PCI SIG website to see what they're at, PCI 4 is pretty much all I've seen so far. I'm sure they probably have an idea of where it's going, right? Because with Ethernet and Infiniband having 400 gig roadmaps and an idea of when they're going to get to that. What's that next? But I think with PCIe 4, you're looking at what, about 126 gigabits per second for an X8 type connection. So I mean that's going to keep us pretty good for a while, I think. So one thing that's interesting is as we start offering these different types of connectivity, maybe you have jobs that are going to run that don't necessarily need 100 or more than 100 or more than 50 gig. You're going to see that we're offering connectivity options where you've got a 100 gig interface, but at the same time that 100 gig interface can be split out to 12 line rate 10s. And I know the math doesn't add up. It's just that on an MTP24, when we're running in a native 100 gig mode, we don't use 2 of those pairs of fiber. If we break it out into individual 10s, we actually get to use those. So that's why we get 120 gig or 10 gigs out of it. Or we can run that in 3 by 40 gig, all out of that same port. And you can kind of interact, you can have say 8 10s and 140 or 2 40s and 4 10s. When you break it out, you get a lot of flexibility. So we see that as being a very good flexible roadmap as you ramp up from 10 gig to 40 gig to 100 gig. This is just a quick snapshot of what our portfolio mostly looks like today, but expect this to change as we move towards the end of 2015. 2015 and 2016 are going to be some pretty interesting years, mainly because what the chip manufacturers are coming to market with. And what our focus is, we don't want to be trying to do what the big, traditional network companies have been, which is try to build our own ASICs and manage all of that, because that's hard to do and it's very expensive. If we can work and consult with the Broadcoms and Intels of the world, that's their business. If they make a mistake on the design of one, it's much more economical for them to fix that mistake and then make that silicon available to us. So our intellectual property is, number one, how do we package that? How do we wrap the right software drivers and architecture around it and offer the right types of features? But all we do is high performance data center core aggregation switching. So that kind of gives you a view of our portfolio. And I would say in most of the large commercial Ethernet-based HPC environments that are out there, this is really one of the areas that Arista shines, and it's one of the areas where we kind of that high performance computing or high frequency trading. Those are 2 areas where we really cut our teeth and got started. So it's definitely an area that we've got a lot of expertise and a lot of very good case studies and showcase customers that are using that. So just in terms of some different architectures, I mean, these are kind of common across different types of technologies, where we can have typically a 2 or 3 tier architecture. We definitely like the 2 tier. It's definitely lower latency, higher performance, whether you start with 2 spine boxes or being able to scale that out. We now can scale out to 64 way or 64 wide spine. So that's, I mean, the numbers that you can scale up to, it's actually double this now with the current software that we have available. In non-oversubscribed versus your typical 3-to-1 oversubscription. So these are some of the references, because again, some of those charts that I pulled down, some of the references that I pointed to for those. And that's it. Anybody else have any other questions? Okay. Well, thanks for having us.